typical application in which we use some of the Flownex rotating components to model a secondary flow path in a gas turbine engine. I also briefly discuss cooling processes and how Flownex can be applied to modeling. In the specific example I'm going to be covering, it's just an airfoil. And then I'll also discuss how Flownex can be linked to an FEA code for full 3D thermal analysis as well. I'll touch on some additional tools in Flownex Toolbox, and then there'll be a demo portion where I bring up a network or two depending on how much time we have, and I'll speak to that. Again, feel free to type any questions into the chat box if any come up. So just with regards to the approach Flownex is taking, so it's essentially solving the conservation equations for mass momentum, angular momentum, and energy to obtain mass flow rates, pressures, and temperatures throughout your thermal fluid network. One thing I really want to stress is that Flownex is a maintained and supported platform that undergoes comprehensive verification and validation with every release. The tool is constantly undergoing development, and every year after year, capabilities are being added to the tool, and those capabilities are driven by requests we get from clients in industry. So we call Flownex a simulation environment, and that's because that attests to the fact that it's highly flexible. So it allows users to implement their own custom flow resistive correlations and heat transfer correlations into the code. So a lot of companies have proprietary information that they've been developing for several years, and they have a need to incorporate that into a platform like Flownex and really consolidate all of their thermal fluid system modeling in a single tool like this, and that's why it's really a great flexible tool. Excuse me. If we look at the Flownex component library, it has, for modeling secondary flow paths, it has a full library of components. Everything you'd expect to see in a secondary flow path in terms of vortices, seals, cavities, nozzles, all of these components that you'd go and link up and model a flow path between a compressor outlet all the way to a turbine blade. And that's kind of what we've done here on the screenshot you can see, and this is a model I'll be pulling up a little bit later and talking to as well. So the whole basic idea is you have these components in your library, and you place them on your drawing canvas and reconstruct a network, specify set of parameters, and simulate the flow path. But the great thing about Flownex is it's really quick and easy to set these up, and you can also investigate the effects of changing multiple parameters extremely quickly. And once you get those results, there's a couple of cool things you can do with them, like use them as boundary conditions for 3D thermal analysis. And I'll be showing you how we do that a little bit later on as well. I'm not going to go into too much detail on every single one of the components in the rotating library, but I will pull out or refer to one or two of them and just touch on a bit of their theory, just so you can get a sense of how Flownex works and what it's taking into account. If we look at turbomachinery cavities, for the most part, Flownex, we use these components in Flownex to model rotor-stator or rotor-rotor cavities. So any cavity where you have a rotating surface that is transferring power to the fluid, and essentially pumping the fluid along or increasing its pressure as you move radially outwards. So the Flownex model, how it really works is it's just doing a moment balance between the rotor and stator, incoming flow, extraction flows, and we can even account for bolts on the rotor and stator surfaces as well. And we essentially do an energy balance, and we can calculate what the windage power transfer is to the fluid for that component. So how each term, here's just an example of how we calculate the moment of the rotor. We can see it's a function of distance from the center line, rotational speed, friction factor. And the cool thing about this component, well, is that you can actually take into account complex surface geometry. So this blue line that you're seeing right there, you can think of as if you can see my highlighter there, it's just the profile of a cavity wall. So we can give it some complex surface specification. Essentially, if we look back at this moment term, increasing the area in that moment calculation and increasing the total windage power transfer to the fluid. Another factor that could further increase windage power is, having bolts or bolts with various drag coefficients on those rotating surfaces as well at different radii. So they use the option to specify that, and even further increasing windage power transfer to the fluid in the cavity. One more thing, just on these cavity components. If you think about, let's say you have a cavity of a certain height, what we can do is we can discretize that cavity however many times we want at various increments. So if you can imagine I've incremented a cavity 5 times every 20% up its height, we can get a look at how fluid properties change as we move radially outwards. So what I'm plotting right here is just total pressure at each one of those points radially outwards. So that's really neat if you're trying to get some sort of profile for how, or to look at how a pressure profile or something like that is changing in a cavity. And also it's critical if you think that you have locations where you're extracting flow out of a cavity. If you're looking at where to place that extraction point or inlet point, that's something that can be investigated by discretizing the component as well. So for the most part now, Flownex can be used not only for modeling just like cold flow, or just airflow, but you can also integrate heat transfer modeling with your flow models as well, to do cooling design analysis. So the simplest way to be that cooling design analysis can be understood is an iterative sequence of several steps leading to an overall model that is optimized for things like material thickness, cooling configuration, cooling flow, and all of that. So if we look at how we progress here, and you take a simple 1D model, simple one-dimensional correlations for heat transfer, and you link those together to come up with something more complex, like a 2D representation of an airfoil, for example, or a combustor, or whatever it may be. So just going a little bit deeper into where Flownex fits in cooling analysis. If we talk about preliminary design steps, more generally, Flownex checks every one of these boxes. In that, it's a way in which you can estimate external heat transfer coefficient distribution on the airfoil, and it includes effects like surface roughness, turbulence. You can either estimate total heat transfer to include radiative heat flux separately, or as part of a lumped effective convective heat transfer coefficient when you're modeling heat transfer to a surface as well. We have heat transfer components for modeling film cooling, and it allows you to calculate an average adiabatic wall temperature. We can represent conduction through multiple solid materials with multiple layers, so you can have your airfoil material, your metal material, covered in a thermal barrier coating or whatever it may be. You can have multiple layers of conduction. We can also estimate internal heat transfer coefficients. So using correlations within Flownex, you can calculate heat transfer coefficients for internal flow. Once you have all of that, you can iterate on a solution to achieve target metal temperatures, thermal gradients, material thicknesses, etc., all to comply within your specified set of constraints when you're designing. In this case, an airfoil, or whatever your situation may be. So I kind of alluded to this earlier, but once you have a simple representation of a section of any geometry, you can knit it together and essentially represent a 2D model within Flow. So we can model heat transfer both axially and radially out of a combustor or an airfoil or whatever that may be, by knitting together all of these components, all these one-dimensional components and correlations. And this is sort of analogous to finite element model construction. So the correlations that the user is applying is major consideration, both for internal flow and external flow and film cooling, whatever section of the geometry you're looking at. And we recognize there are numerous amount of internal cooling geometries, and all the parameters that need to be taken into account are vast, and because there are so many possible combinations and variations, and people approach this so differently, we've really set out to make Flownex as flexible as possible, and make it as easy as possible for a user to incorporate their own specific correlations into Flownex itself. That being said, we do have several generic correlations that have been built into Flownex already. Correlations for film cooling, impingement cooling, gaseous radiation, forced convection, everything you would expect to need to model the heat transfer and gas turbine applications like this. But again, I just want to stress that implementing your own correlation is very straightforward. So once you have a Flownex model set up and running, in many cases people want to use those results or those thermal loads as boundary conditions for a 3D thermal analysis. And there are ways to, automate the mapping of bulk temperatures and heat transfer coefficients from Flownex, from your one-dimensional model to a 3D model in ANSYS. And how you would typically do that is you would have Flownex output a file of thermal boundary conditions, and then you would have your FEA tool, in this case ANSYS, read and map those boundary conditions to a 3D CAD model. So once that's all set up, it's pretty straightforward to investigate different operating conditions and design changes in a way that is not tedious and really quick, and it's really where you're getting the best of both worlds. You get the speed of 1D simulation with the accuracy of a 3D simulation. When it comes to Flownex customization, there are a couple of ways that we can create our own components and databases in Flownex. So let's say, for example, you have some custom flow resistance. In this case, the equation you see here is just a mass flow rate pressure drop relationship for an axial swoller. And if you want to represent something like that in Flownex, in your own Flownex library, you could do that using Flownex scripting. So the scripting language is C#. So you could easily go and script in this little relationship or this user-defined function. You could then go store that in a custom database that is accessible company-wide by all Flownex users within a specific organization. So the real takeaway I want you to get from this slide is that you can really use this as a platform on which to really build quite a great library of components that you can use in-house that are specific to you, and you can really grow on that, and it's easy to maintain and yeah, easy to share across the company. If we look at just some additional tools in the Flownex toolbox, there are easy and quick ways to run parametric studies. There's a designer tool, which is basically like a goal-seek function. So you can optimize parameters in your network to get certain to obtain certain desired states. So let's say you wanted a certain mass flow rate through a section of a model, and you wanted to vary an orifice size. You could specify what you wanted that mass flow rate to be, and you would give your orifice size a range through which it could vary, and Flownex would iterate until it would get to that set point. There's also an optimizer tool which allows you to minimize or maximize certain component or system parameters as well. Just one more point on the parametric studies. So there's Excel-based parametric tables and input decks in Flownex as well that make running through several hundred cases with different different parameters really quick and straightforward. Before I bring up a demo network, I just want to stress again, why Flownex. For one, it's a 1D thermal fluid network tool that employs conservation, mass momentum, and energy. It has a user-friendly interface. It has an open architecture which makes it easy to link to third-party FEA or CFD or post-processing software. It has a library that employs industry standard correlations for gas turbine heat transfer. It also has a complete library for modeling secondary flow and heat transfer paths. Its scripting capabilities make the tool flexible and very straightforward for someone to specify their own user-defined functions. The solve time is really quick, and the solver is extremely stable, and it's really straightforward to set up parametric runs for your network models as well. So with that being said, I'm just going to run through this model I spoke to a bit earlier. So again, here we have an extraction point just after the compressor, and we have various components that we use to model various geometric features in this flow path. So you can see we have a restriction at the inlet here. We're able to specify both swirl boundary conditions and fluid boundary conditions. With regards to the temperature and pressure boundary conditions, we can specify both static and total pressure, and we can specify inlet temperature and then also a swirl at this point. And then we can go down and represent flow losses and power transfer to the fluid. Here, for example, we have a rotating cavity or a rotor-stator cavity. We can define that that cavity profile. We then come into this section where we have, a rotating annular gap. That splits off into a rotating nozzle, and so on and so forth. It's pretty straightforward. I'm sure it speaks for itself. There's one area that I just wanted to point out particular interest in, that is this specific cavity, which I've discretized every 20% of its radial height. So we can see we specify the inner and outer radius. So it's essentially the radius at the bottom of the cavity and the radius at the top of the cavity. We can then take a look at the results at each point as we move radially outwards. What's really nice is integrated within Flownex are these Excel reports. So I can just drag and drop specific increment results. So let's take all 5 increments and let's take their total pressure, for example, and I can put those in a Excel report in any format that makes sense for me or that I like. I can go and give this labels and set it up however I want. This one that I have set up before, I have plotted out the cavity pressures as we move radially outwards here. So we can see how those increase. That's pretty neat. One other thing we can do is set up these parametric tables. So I have multiple conditions here. So you can look at each of these rows as a specific design point, and you can run through your model and have Flownex essentially output conditions at each one of these results. So for different upstream, downstream pressures, different rotational speeds, I can run through that model and it will populate a table with results for each of those cases. So let's go and run that and see what happens. So we can see it takes the model a couple of seconds to solve, and every time it's running through each of those cases I've specified previously, I can see what my pressure results are in the cavity. And again, the great thing about this is you have full control of what parameters are important to you, what parameters you want to vary, and also the format in which those are being output. It looks like a little short on time. I just wanted to touch on the scripting capabilities real quick. So just within Flownex, we have these components, which we call script components, and they're essentially full parsers and compilers of Microsoft C#. So if you're not too intimidated by the programming language, what you're able to do is, completely come in and script in your own user-defined functions. So let's say you have some flow resistive relationship you want to come incorporate into this model. So you have, I don't know, some proprietary lab seal model that you've been developing for 20 years, and you want to come incorporate that into a model like this. You can do that quite easily with the scripting functionality. And then again, there are a couple of neat ways to store those scripts or those custom components in your library of components, and you can access those at any other point and use them in across multiple models as well. I'm going to give a few minutes for questions, and if you have any, please type them into the chat box or raise your hand. We'll unmute you and we can address any questions that you might have.
We have a question here, if you just want to have a look. Another question box from Ashish Nahi.
Do you mind reading it? I don't think I can see it as in my chat
yes,
window.
in fact, I'm going to unmute you, Ashish, if you want to discuss it verbally. The question itself says, yes, we can hear you fine.
Yeah. So the question is, it happens that sometime in the preliminary design, when you just started for a model, you may come across some resistances which are not flowing. You have zero flow or zero pressure difference across those. So how does Flownex numerically handle this? Is it possible to solve such models in Flownex?
Certainly. So we actually have, if you look in your flow resistance library, so we have a section called custom losses. So that's a way you can represent, losses in Flownex in several different ways. So let's take it, for example, a flow resistive element, because it's something I would use in a scenario exactly like you described, where you might have a section where for a time being you don't necessarily want to model a pressure loss, or you don't know what a pressure loss might be, or you just want some sort of approximation of what that would be. And this specific component you can think of as it's pretty straightforward in its description. It's just flow resistance, and what it's looking for is a flow admittance value, and that admittance is sort of like an electrical admittance, in that giving it a very large value, like say it's a 10,000 or a million. So if I give that component a really large flow admittance, the resulting pressure drop will essentially be zero. Because if I look at the pressure drop relationship for the specific component, it's a function of that admittance. So we can see for a high admittance value, which is below the division sign, we'll essentially have a zero pressure drop. Does that answer your question?
Oh, yes.
Do you have any other questions?
Yeah, one more. So which particular ingestion model are you using in this demo model which you show here? Is there an ingestion model?
Sorry, what word is that?
Well, near the sink of this model, where the coolant flow is merging with the hot gases, is there any ingestion as such modeled?
No, that's not being modeled at all. Yeah.
Okay. but as you said, Flownex does allow you to input your to write your own script to allow such model. Is that correct?
Yeah, I believe it is possible. I just don't think I understand what exactly it is you're trying to model at that point. Maybe if you can explain to me, I could answer your question more confidently.
Okay, so what I mean is you have just upstream of the rotor near the hub, uh, there will be some hot gases ingressing inside the cavity,
Oh,
which
ingressing. Yes.
yeah, it will heat up the gas and eventually the disk
Oh,
surface as
yes.
well. So how is that? How can one do that through scripting? Because it's not just defining the losses for a given element or resistance using script, but it's interaction of different different flow paths. It's little complicated scripting.
Oh, sorry, understood. I didn't quite hear what you were saying, but if we look at, so integrating, this is essentially just a cold flow model right now. And by that I mean we're not modeling heat transfer to any solid portions of this model. So all of these components represent um, only the flow path. Let's say we want to represent, some solid or some heat transfer in this component. So what you would do is you would grab from the Flownex library here, from the heat transfer library, you would, and this is just one of this is just one of the ways you would do it. The scripting is always an option, but let's take, for example, this composite heat transfer component. So you could link that to these flow components, if that makes sense. And this guy allows you to define essentially a wall here through to which you're going to um, convect gas or radiate, convect heat or radiate heat, or whatever your heating mechanism may be. You can represent that heat transfer with this component. So um, what this component is going to do is, if we look upstream, we can specify a mode of heat transfer. So that can be convection. And then we can also specify an HTC value, a heat transfer coefficient. So that can be either calculated by some user-defined function, user-defined scripting, that HTC value, or you could use one of the correlations that are already within the tool. Is this sort of answering your question on the right track here?
Yes, it does.
So, we could link that guy. We could say, okay, in here we're going to assume this is, say, Dittes-Bolte or internal flow. We're going to assume that correlation, and Flownex will then calculate a heat transfer coefficient. It will then also calculate a surface temperature based off of what the bulk temperature is here and what that heat transfer coefficient is. Does that make sense?
Yeah, it does. Sure. Thank you.
So, I mean, if you have, do you have any other questions?
No, that's all for now.
Um,
Okay, super, Stephen.
Yeah.
Are we going to close the webinar?
Yes, I don't have anything else to add. Thanks.
Perfect. Well, thank you very much. That was great. Yeah, I hope everyone received what they wanted to from this webinar. We'll have a recording of it available as well if you'd like to go over anything. If you'd like to just keep have some further contact with us, if you'd like to, if you have any further questions regarding trialing the product or anything like that, please feel free to contact us. You can respond to any of the registration emails. But thank you very much. Thank you,
Sure.
Steven. That was super. We'll keep in touch.
Thank you.
Okay. All the best. Ciao, ciao.